Micromodels are used to simulate flow through porous media. The experimental device is something very much like a microscope slide, a piece of glass that is etched with a particular structure in it. It's transparent, and so once it's etched, the top piece of glass is put on. So you've got a thin structure that has pores in it and can have fluid flowing through it. So we see here on the left an experimental device that has a micromodel in it. The micromodel itself is right in there. And you can see that the window on this is transparent so that this micromodel can be visualized during an experiment. Flow is put in this side, and there are two inlets for putting in two different types of materials so they can come in and mix in this particular example. And then they go out here. And if we zoom in on this micromodel, we can see that in this case, it has this very regular geometric shape. It's these cylinders that are a few tenths of a micron high, and these are etched out of silicone, and this is the pore space right in here. In this case, we also have cylinders, but there are big ones and there are small ones right here. But this case is also an example of a very regular array of solid materials and a very regular pore structure. And in this case, what you see is this black material. These are bacteria colonies that are forming in the pore structure during an experiment. So some kind of a reactive fluid is put in there. It causes the bacteria to grow. And the real beauty of micromodels is that because they're transparent, you can view the processes that are occurring within the pores. So here is a picture of the design of the micromodel that we saw on the previous slide. This is the pore structure right here, and there are two inlet ports. And in this particular case, this micromodel is made to study the mixing and reactions that occur between two fluids that are put in these two ports. It goes out, and then the outflow mixes here. This is a scale 1 centimeter. And if you magnify this area, the pores look like this. These are the solid grains, that's 300 microns across, and the smaller one is 135 microns across. And here is the dimension, 40 microns there, 180 microns from one surface to the other surface of these larger grains. So this gives us the dimension of the pores and the solid materials. This is from a paper by Ostrom et al. That was published recently. And we'll use this as a basic model. Now, in the paper, the model was made of this entire pore structure, but we're going to just take a smaller piece of this structure and make the model of just a small representative section. We can make that model bigger and represent many pores, but for our purposes here, I want to show you how to set up this kind of model, and we want to stick with a model that's relatively small, and so it will run fairly quickly. So here are some specs from the Ostrom paper. They ran various experiments here with different flow rates, different velocities, and here are the grain diameters, and so you can see the 300 micron grain diameters. Those were the model. That was the model we just saw, but there are some other sizes here. They calculated Peclet number, and they also calculated an effective diffusivity here. So here's the initial model that we'll set up. These are the solids, and you can see the pore structure here in the blue color. These are the specs. The large grains have this diameter, small grains this diameter. This is basically from the paper that we just saw, the gap. And then I set it up so that the pressure on this face is 1 Pascal, and the pressure on this face is 0 pascals. So we'll use specified pressure boundaries. And here are some of the results. The color contours here are pressure. So it goes from 1 to 0. Here's the scale. And you can see that the contours are roughly straight here. And they kind of cut through the pores and cut through the grains. The pressure gradient, however, is not uniformly distributed. This is the pressure gradient, and here's the scale in Pascal per meters. And you can see that through much of the pore structure, the pressure gradient is relatively small. But then right here at these pore throats, where the diameter, or where the gap, basically the diameter or the gap, the width of the pore is smallest, that's where the pressure gradient is largest. So we have very small pressure gradient throughout much of the pore structure, and then the pressure gradient that we would see over, or the pressure drop that we would see over this entire experiment was really a result of pressure drops that occur over several localized areas. So that's somewhat of a different view than we get when we use the homogenized view of a porous medium. So this is the velocity magnitude, and you can see that the velocities increase as you reach these gaps, these small gaps between the grains, and then the velocity drops here in the larger gaps. These zones right here are relatively low velocity zones. In fact, right in here it's stagnant.